Hello, everyone. Welcome to the second part of the AI agents track at this AI and Gaming Research Center. My name is Diego Pérez. I'm a senior lecturer on computer games and AI in the Game AI group at Queen Mary University of London, and I'm honored to be the chair of this second part of the session. During this track, we'll have very interesting three talks in this talk. The first one will be given by William Guss and Stephanie Milani. William is a research scientist at OpenAI, and both of them are PhD students at Carnegie Mellon University working on machine learning. In their talk, they let us know about the MineRL competition that ran last year. And as Katya said during the keynote, we'll get to know the winners of this competition, which is aimed at improving sample efficiency of reinforcement learning methods. After them, our second talk will be given by Martens, who is an assistant professor at NC State University. Dr. Martens is the director of the POEM Lab, which studies computational models of narrative digital games and co-creative human-computer interactions. In their talk today, they'll talk about abstractions for social agents. And our final talk for this session will be given by Adith, Swaminathan, and Broll. Adith is a senior researcher in the reinforcement learning group at Microsoft Research AI, and Brian is a research scientist at Vanderbilt University. They will talk today about designer-friendly machine learning and reinforcement learning for video games. As in the first part of the track, we'll watch all talks first, and then we'll have our Q&A session with all the speakers at the end of this part of the track. So please drop the questions into the moderated Q&A as you think of them, and above them, if you especially would like to hear the answer for those questions at the end of the session. So I believe we are ready to start with the first talk by Will and Stephanie. So it will be played for you now.
Hi there, my name is William Guss, and today I'm going to be presenting on the MineRL Diamond competition on sample-efficient reinforcement learning using human priors. This competition was organized by a collaboration of OpenAI, DeepMind, Microsoft, AI Crowd, Preferred Networks, and Carnegie Mellon University. There have been a number of collaborators that have come together to put this thing into running shape, and we couldn't have done it without them. Our advisors have been absolutely wonderful in this process of steering the competition in the right direction, and we are so grateful to have worked with them. So I'd like to tell you about why we started this competition. It all starts with one line. Deep reinforcement learning has a sample efficiency problem. If we take a look at the way that ML systems and RL systems have required compute to solve harder and harder tasks, we see an exponential trend. Exponential compute solves RL problems, and we've seen some absolute landmark results because of this. OpenAI 5, Alpha Star, incredible multi-agent control in zero-sum games with extremely long time horizons, competitive with real players. But large-scale RL requires a massive number of samples from the environment. Training OpenAI 5 requires hundreds of years of environment samples a day. AlphaGo required upwards of millions of Go games. And this has two major effects. RL algorithms, first of all, that are developed to solve these tasks have a large amount of difficulty being applied to real-world environments. For example, with robotic grasping, without using sim-to-real techniques or domain randomization techniques on the simulator, we need to have several hundreds of robot arms to do parallel rollouts and so on, so on-policy optimization becomes difficult. And beyond deploying these RL systems in the real world, we have further issues. Many sophisticated RL systems can only be trained by a decreasing few in the community. And this will become blaringly apparent as we try to solve new tasks. However, there are solutions, one of them being utilizing human priors. Algorithms that better utilize human priors are a compelling solution to sample inefficiency. We can drastically reduce the complexity induced by exploration. Sparse environments can often become tractable in the off-policy setting. And spurious credit assignment can be mitigated. Furthermore, algorithms that better utilize priors are a compelling solution to sample inefficiency. First of all, data can be shared and open access, but compute resources cannot. Training RL systems in many real environments can be extremely costly. So we decided to form this competition to galvanize research in this direction. We want to foster the development of sample-efficient reinforcement learning algorithms while providing open access resources that can be shared amongst the community to democratize access to training these algorithms. This competition we propose, the 2020 MineRL Diamond Challenge, was a follow-up to the 2019 MineRL competition on sample-efficient reinforcement learning. And today I'm going to tell you about this challenge and how it has translated into galvanizing this research. Competitors in this challenge were given the hard task of finding a diamond in Minecraft. Minecraft is a compelling domain. It's 3D, first person, and open world. There are hierarchical, sparse, and long time horizon subtasks. It's potentially highly multi-agent, and there are an infinite set of definable reward functions. There are many different objectives players choose to seek, and all of them can become RL benchmarks therein. In our challenge, competitors must train an agent to obtain a diamond. This is a very complicated task. It involves several steps: gathering wood, so navigating around the environment searching for a target object, spending time chopping down that object. Then, competitors need to go through the complex item hierarchy of Minecraft, create wooden pickaxes, mine certain materials, mine iron ore, create furnaces, so on and so forth, and eventually search to find a diamond in Minecraft. Agents are rewarded for achieving items along the item hierarchy in this 16,000 time step task. We assign exponential point values to each item, and the rewards are assigned immediately after the agent obtains the item. These rewards accrue linearly over the trajectory of an expert agent, as each task is exponentially harder than the previous. So to really promote sample efficiency research, what we do is we require that submissions only use 1 GPU and 4 days of training, with a limit of 8 million actions in the environment. Now, these numbers are so drastically smaller than traditional RL competitions, we wouldn't expect any meaningful policies to come out of it. But you'll see, and as in previous years, they do. To guarantee reproducibility and general solutions, we don't evaluate agents, we evaluate training. So in round 1, competitors will train their agents on their 1 GPU with 4 days, 8 million samples, and submit their agents. These agents are evaluated over 100 episodes and scored. Then the top 10 scenes are taken from round 1, and in round 2, competitors submit training code, and the domain is completely randomized. We change the texture pack of both the environment and the dataset, and then we train their agents from scratch. You can see here on the right-hand side that competitors, after being evaluated and trained in this new environment, still is robust and still performs, meaning that there were robust and general solutions created. Now this year, we've done something a little bit different. To prevent hard coding and force domain agnosticism, we obfuscate the actions and observations. Typically with an RL competition, we provide the action space, the observation space, and what we see is a lot of solutions spend a great deal of effort imputing inductive bias on the problem by shaping the actions or extracting the right features. And what we really want to promote here is generally sample-efficient algorithms. We want to benchmark them and promote their development. So we do this action obfuscation step, wherein we take the original action space and all the possible set of actions, as well as the set of all observations besides pixel observations. And then we train a completely random autoencoder with as high reconstruction fidelity as possible. Then what we do is we take the environments and serve all of the observations and actions through this autoencoder and basically provide a random embedding for the participant's solution. What this looks like in practice is a POV observation, as you can see here, and a state vector and an action vector, continuous action vector reflecting all the actions. In addition to all of these mechanics in the competition, sample efficiency research, as we said, can be galvanized by large-scale data sets of human priors, and this is domain agnostic. So we provide competitors with a large data set of embodied human demonstrations, the Mineral v0 dataset, with 60 million samples of Minecraft tasks across 6 different tasks. We also provided competitors with a synchronous fast Minecraft simulator. You can check out the simulator by going to mineral.io, reading the docs, or pip installing it yourself. Now, I'm going to discuss the results of round 1 of the 2020 Mineral Diamond Challenge as of recording. Round 1 has over 323 submissions, and teams are doing well despite this action obfuscation. We can see that we've made substantial progress towards obtaining a diamond, with the highest teams obtaining stone, which is just a stone's throw away from this diamond result, and many of the subsequent teams getting pretty far into this item hierarchy.
And now, I'll be presenting the results of round 2 of the 2020 Mineral Diamond Challenge. In round 2, participants achieved even higher scores than last year. The first place team achieved 10 points higher than last year's, even in the face of our new obfuscation step. Additionally, both the imitation and reinforcement learning track fared well against the round 2 change in texture pack, environment dynamics, observation, and action spaces. In comparison to the first round, competitors were much closer to obtaining a diamond. The first place team, sitec.de, trained an agent which repeatedly obtained an iron bar, while both the second and third place teams solved the hard exploration problem of getting iron ore. Given the substantial progress this year, we believe it's likely that algorithmic progress enough will have been made to achieve a diamond in the next iteration of the mineral competition.
And now I'm happy to announce our first place winners. For the main track, we have team sitec.de. For the imitation learning only track, we have team Michal Upanowicz. Congratulations to our winners. Each team will receive an NVIDIA Titan RTX GPU. Additionally, we have 2 auxiliary prizes, the Research Award and the Community Support Award. For providing extensive support and advice to the competitors, we are happy to give the Community Support Award to Ansi from Team No Action Wasted. For developing a unique and innovative approach to addressing the mineral challenge, we are happy to give Team SIT-ECDE the Research Award. Each of these awards comes with $500 of hardware. Congratulations!
With the prizes announced, I'm very excited to introduce the Research Spotlight Talks from the top 3 teams. With a score of 72.510, please welcome SIT-EC.DE.
Hi, my name is Andrew. Our team participated in the Minecraft competition as a part of a semester project at Bielefeld University in Germany. In our work, we aimed to learn to detect objects using rewarding signals of interactions with the environment. We generate masks over reward-related objects in an image using a UNet model. The UNet model learns to segment tree trunks without any label information, but only from reward signals in a contrastive fashion with image pairs using an adversarial scheme employing the critic score gradient with respect to the mask operation. The critic learns to estimate the expected reward value of an image observation using experience replay buffer collected from human player demonstrations. Our approach of training the UNet model showed encouraging results of segmentation of rewarding objects in the MineRL competition. It generalizes well between different tree types and is robust against false positive detection in frames without tree trunks. Here is the explanation of the training procedure. First, we select image A with high critic value. Then we pass the image through the UNet, and UNet produces a mask of a rewarding object in image A. Then we randomly select an image B with low critic value. We take the mask produced for the image A and mix images A and B with respect to the mask. As a result, we get 2 mixed images, X and Y. In the next phase, we feed independently all 4 images A, B, X, and Y through the encoder and bottleneck part of the UNet, and then through the critic. With that, we obtain critic values for images A, B, X, and Y. The losses shown in orange penalize a difference in critic values for image pairs A and Y and B and X. The backpropagation path for these losses is shown in orange. The mask size loss shown in black prevents a trivial solution when mask takes the full image. With that, I would like to thank you for your attention.
Next up, we have the first place team from round 1, Hello World, coming in with a score of 39.550 and second place in round 2.
Hi everyone, we are the team Hello World. We are from Tsinghua University and Huawei know us Arc Lab. My name is Chen Jie. I'm glad to share with you our efforts to deal with the MineRL task. Our task submission scores about 39 and is ranked number 2 on leaderboard. At the core of our design is a hierarchical architecture. MineRL task is of strong temporal dependence. That is, the successful execution of one stage depends on success of all preceding stages. For example, it is impossible to craft a pickaxe without collecting enough logs. Additionally, sub-policies vary widely. They depend on different aspects of information revealed in states and should be trained towards different goals. So, we split the stages according to accumulated rewards. We train separate networks for each stage and train a meta-policy network to choose between these sub-policies. Here is an illustration of our framework. As you can see, expert demos are split into stages and are fed to corresponding subpolicies. For each subpolicy, we test several reinforcement learning or imitation learning algorithms. These include behavior cloning, BCQ, SQIL, DQFT, POFD, and Rainbow. We choose the best tuned algorithm for each stage. In our experiments, we find pure reinforcement learning algorithms are not comparable to algorithms that utilize demonstrations, which is expected because the environment is super complicated and requires long-term planning. DQFT, pre-trained only without environment interaction, always outperforms behavior cloning. SQIL, incorporated with self-imitation, can avoid performance drop in training. That is, we put successful trajectories collected by the agent into the demonstration buffer. Here are some tricks that we find may be helpful. First of all, pre-training. Pre-train agents on simpler environments, then transfer to the obtained diamond environment. The second one is representation learning. We can add auxiliary tasks to let the agent learn object segmentation and recognition. And tuning action clusters for each stage also helps. Applying state augmentation may make the agents more robust. When something is not expected happens, replays recorded may tell you what is going wrong, so do remember to watch the replays. Because the environment is of high variance and results from consecutive evaluations seem correlated, we think that we should run more evaluations before discarding any potential improvements. Last but not the least, every little helps. They may finally constitute a big leap. That's all. Thank you.
Finally, I'd like to introduce our third place team, Michał Panowicz, with a score of 13.290.
Hi, my name is Michał Panowicz, and in this presentation I will show you how I approached MineRL 2020. So first, some thoughts about MineRL. The problem is very hard. The competition's goal of learning to acquire a diamond should be quite difficult, even for a human, I think, if they didn't have any prior knowledge about Minecraft. The replays are quite noisy, and many of them don't actually show player finding a diamond. But last year, a relatively simple behavioral cloning approach has reached the second place. This year, the task is harder than last year because of the action being outcoded as 64-dimensional vectors that we can tamper with. But still, I thought probably doing something based on the last year's behavioral cloning approach would result in quite a high score. And that was in fact the case. So now about my architecture. I use FixUp.net for visual processing. FixUp is needed to allow for learning with LSTM, because otherwise batch normalization could provide information for the LSTM about the future states. I use LSTM, which is quite big, with 1024 units, and it is trained on sequences of length 100 without skipping thread. I use k-means to discretize the action space, similar to the baselines. This allows me to use standard cross-entropy laws, basically predicting what a human player would do given some string of observations. I use only obtain iron pickaxe and Richard datasets because obtain diamond shows players doing very difficult to repeat strategies that often involve going into villages or maybe searching for canyons where players can go deeper really quickly. And finally, I use data augmentations, transposing and flipping the images vertically, because we can't flip them horizontally, because flipping horizontally would require modifying the action space. I also use permuting color channels. This data augmentation seems to slightly improve performance, but very slightly. As you can see, the agent performs somewhat well and can collect a stone in around 20% of runs. Collecting stone pickaxe is surprisingly difficult given that it can collect a stone. So what didn't work? Directly predicting the action as the network output basically failed. Similarly, trying to sample the action from multivariate Gaussian distribution or a mixture of such distributions also failed. In general, Gaussian distributions seem quite difficult to train and do right. Surprisingly, also predicting how many times to repeat an action instead of observing every frame didn't improve the performance. The agent still learned, but it wasn't as good as predicting basically the action every frame. So thank you for your attention. There is a link to a poster, and the code should show up soon at my GitHub. And thank you to the organizers for this quite unusual competition.
Thank you to AI Crowd and Preferred Networks for helping us run the competition. Thank you to our sponsors who made this competition possible. We retrain submissions, which requires a lot of compute. Thank you to Microsoft Research for enabling us to do this. We help members of underrepresented groups participate by providing compute grants and NERPS registrations. Thank you to the Journal of Artificial Intelligence for funding this. And thank you to Microsoft Research and NVIDIA for providing prizes. We also thank our advisory committee. The MineRL competition seeks to promote research and sample efficiency, and input from our advisors is crucial in achieving this objective.
We've seen great progress this year in the ability of the agent submitted, but there remain many challenges that can be tackled with this environment and dataset. We encourage everyone watching to consider participating, as finding that diamond remains an open challenge. If you prefer not to compete, there are still many ways to positively contribute to the community's progress. We encourage you to reach out if you would like to co-organize or collaborate on the competition. Thinking beyond the competition, perhaps there are ways this environment and dataset can be of use in your own research. I'm personally very excited about the potential of utilizing this dataset to validate approaches that mimic human playstyles without needing to be explicitly trained on that data. Alternatively, perhaps the environment of Minecraft can provide other challenges for AI. There were some interesting examples of this in the talk earlier today by Christoph Sauge on generative design, and there's the upcoming EvoCraft competition exploring open-ended creativity in Minecraft. Finally, if you're in the position to open up another game or gameplay dataset for everyone to experiment with, I would highly recommend doing so, as it is a very engaging experience and a great opportunity to learn from the distributed expertise of the whole community.
All right, fantastic. That was a very, very nice talk. I'd like to thank the speakers for the talk. Also, congratulate the winners of the competition and the run-ups as well, and also the organizers, because it's organizing this sort of competitions is a lot of work, and showing that you have had already more than 300 submissions in a very, very new competition. It really shows how well designed and how much work was behind it. I'm already receiving many questions from the production team, and as a reminder, we'll answer all these questions at the end of the session for all the talks together. But now we can progress to the next talk. So we have now Chris Martens, who will talk about abstraction for social agents. So whenever you're ready, Chris.
All right, thanks. Hi, everybody. I'm happy to be here. My name's Chris Martens. I am an assistant professor at NC State University, and I direct a research group called the Principles of Expressive Machines, or Poem Lab, at NC State. And this is work that I want to present to you. It's really kind of work in progress, as we indicate in academia by putting a towards before our titles usually. But we've got some, I think, exciting preliminary work going on. And I especially want to thank my PhD students, Sasha Azad and Jennifer Wellnut, who have been a huge part of this work. So they're also collaborators on what I'm about to show you. So what we're trying to address is basically a challenge when it comes to player experiences of non-player characters in games, especially when there are several non-player characters in a game. And there are kind of two problems that tug against each other, right? There's what I like to call procedural legibility, or basically the ability for a player to form an intention and a plan towards achieving that intention by creating an accurate mental model of what the game responses are to player action, and that they should be able to learn sort of how those interactions form a game mechanic that they can engage with. And the other one is social believability. So I think there's kind of this, at least intuitive understanding that we want our NPCs to be, they don't necessarily have to be super realistic in the sense that we would expect to, encounter similar characters as human beings in the real world. But if we want to tell stories with characters, right, they should have kind of legible goals and flaws, charms, and potentially character arcs, right, ways that they change and improve over time. In most classic NPC models, social character or NPCs will basically stand around doing nothing until the player approaches them or comes within a particular radius or whatnot. And this leads to a model that where we can't really tell stories about very complex social dynamics, things that we might watch a really good movie about, usually involve a lot of things like trust, betrayal, love, and heartbreak. And you can tell stories about these kinds of things with a cutscene, but we're kind of interested in how can these social interactions arise as emergent properties of social simulation systems. So the question here is kind of, can we do both? Can we have our cake and eat it too? And this is where the sort of concept of social agents comes in. And part of the problem that we're addressing here is that social simulation, social agents, there isn't really a consensus definition of what this means. People will use this term in various different contexts to refer to a lot of different types of simulations, types of real world phenomena that we are trying to simulate, as well as even when they agree on which real world phenomena they're trying to simulate, kind of approaches to simulating it and what simulating it actually means, kind of how, what level of abstraction to present it at. So this is an example of 3 different games, Prom Week, one of the Sims games, and Animal Crossing, which are all kind of ways that the game communicates to the player. What's going on is a brag interaction. So one character is bragging to another character, but these are all communicated very differently to the player and create very different kind of state changes in the relationships between characters themselves. So when I say abstractions, right, abstractions for social agents, I care about abstractions fundamentally because I'm trained as a programming language designer, and I am often frustrated by kind of finding these very like strongly overlapping sets of tools for implementing social simulation, but where everyone's kind of reinvented the wheel and kind of done their own thing. The folks at UC Santa Cruz behind Prom Week and so on have this term I like called, where they say what they're after is kind of a social physics engine, or by analogy to the idea that we have physics engines that can be reused to tell lots of different stories. We should be able to have some kind of social interaction engine, a reusable library of primitives to build social simulations with. And I'm not the only one, of course, who wants this, but I don't think we've really achieved that so far. And part of the way that I approach that is kind of as a programming language design problem. They're trying to figure out, okay, what are all of the common primitives that we need to be able to put together a rich palette of stories? And can we kind of formalize that as a domain-specific language, or even just an API or a library that can coordinate with lots of different tools. I also really care about authoring tools, so things like usable programming environments and editing tools come into play as well. So with that, the scope of what I'm talking about in this talk, just to give you kind of a sample of games that I consider to be in the social simulation space, include all of the Sims franchise, lesser known games like Tiniest Shark's Red Shirt, where you're communicating on a fictional social network called Spacebook, and things like Prom Week, which were developed within academia, but were at least for a time playable through like Facebook's apps system and on the web, as well as things like down in the bottom right, we have a screenshot from Blood and Laurels, which was a game developed on the social platform, the social simulation platform called Versu by Linden Labs, which is sadly no longer active, but they had a really cool project in that system kind of pertaining to like conversation dynamics amongst characters in stories. So what is really key to a lot of these different genres is, or a lot of these different games that, you know, kind of share some things in common but not others, is that they center conversation as gameplay. And Emily Short has a fantastic blog that if you're interested in this kind of thing, you should read in general, but in particular, she has a whole talk that she's given about conversation as gameplay, kind of using conversation as a game mechanic. And again, we see that come through in all kinds of different like modalities. So that could mean typing out a text message. It could mean, you know, doing a kind of choice-based dialogue system. And in the case of Versu, right, it was choice-based, but the choices were all procedurally generated by the state of the simulation. So within all of these examples, we not only see conversations, but we see that conversations have some kind of effect on things like character relationships, on the kinds of information that different characters know, their emotional states, and how they make decisions. Basically, it's about people influencing each other through interaction. These are kind of the real world phenomena that a lot of these simulations try to simulate. So in our recent work, we've developed a taxonomy of 8 academic experiments and 2 commercial games that kind of tries to take into account a lot of the different forms of social interaction that people have tried to codify and isolate some of the more common ones. And that is kind of the next chunk of the talk that I'm going to talk through. So first, we have this concept of social state, right? This is just kind of what are the aspects of the game state that need to track things pertaining to our social simulation. And so I've mentioned that this includes things like relationships, knowledge, emotion. It will also include things like character stats, right? Things that pertain to an individual character that might affect how they respond to a social interaction or what kinds of social interactions are available to them, including skills and abilities, things they might have in their inventory, resources more generally, and any goals that they might be working towards with their actions. So this is just kind of like a depiction of kind of an example social state. This is in particular for like kind of a conversational state, which is tracking the previous topic, the next topic that's queued up for a given character, the mood of that character, the sympathy of that character towards the player, and so on, some other features. In addition, we have this concept of social actions, which is basically what are the verbs in your game, not just the verbs that the player can use, but the verbs that the non-player characters might enact between each other, or that the player might decide to enact between 2 or more characters. So these include things like conversational moves, but also things like observation, individual actions, any decisions they make that might affect other non-player characters in the environment around them, and also things like joint decisions and kind of collective decision making, which makes things interestingly complex sometimes. And then finally, we can kind of get to like a definition, you might say, or at least a collection of desiderata for social simulation, which are, you know, the common things that we see in all of these settings are that we have communication done through different modalities, and that can be both a diegetic modality in the sense of like, are they simulating verbal, physical, or gestural communication? It can also be in the terms of how they communicate to the player, right? Are they communicating through static images, like in a visual novel where you just have an image that changes, perhaps to reflect a different facial expression? Is it just through text, or is it through animation? A lot of the kind of interesting innovation in social simulation has happened in text-only games, or at least primarily text-based games. And so kind of navigating this relationship between like these different real-world communication modalities and what medium you're trying to communicate to the player with has created a lot of interesting tension. We see social dynamics like relationships kind of having a charge and decay values over time. So it's not just the social interactions that cause changes to the state. It's also just the passage of time can cause characters to need things or forget things or weaken their relationships and so on. There's things like initiative taking and resource contention, external events in the world that might influence them. And then finally, there are things for pertaining to how the player can interact with this all, right? Like, are they able to do fine-grained kind of selection of what utterances they want to make in a conversation, or is it represented more abstractly with just a single verb, like brag or insult? And then are the player is the vocabulary of player interactions the same as or different from the non-player character interactions that are available? So conversational moves, I used this term earlier, is a term from kind of like the theory of discourse amongst humans, right? Like in social science, right? People kind of study how people carry on conversations with each other. And it's usually in game design terms, again, it kind of translates into the set of verbs that are available when characters are in conversation with each other, including when the player is in conversation with a non-player character. And this may include things like asking questions, sharing information, sharing opinions, and it may also include a bunch of examples tend to influence the relationships between characters. So characters might have positive interactions when someone gives them a compliment, or somebody might insult them, creating a negative relationship, right? But then these kinds of things are all much more complex than just do they have an outright positive or negative impact on the relationship, because obviously if you're just going to compliment somebody over and over again, that's not something that's just going to increase your relationship value with that person forever, right? So operationalizing all of these conversational moves is often a key aspect of what social simulation engines do. I mentioned kind of these conversation modalities. So when we communicate with each other in the real world or even over the internet, right, we have options about how to do that. We can use our mouths and our voices. We can use text. We can move your hands around a lot like I do, use gesture. And then there's like physical, touching kinds of interactions as well, things like hugs and handshakes. And less nice things as well that you'll find in some of these simulations. I mean, interestingly, in social simulation games, the physical is often like not as centered, whereas a combat-centered game, right, like physical interactions are kind of the main thing. Okay, and then we've got relationships. So we found that in the simulations we surveyed, and by the way, I'm not going to go through like the whole taxonomy here. There was a lot of meat in that that we found, and so I'm basically just going to try to give you some of the some examples of common features that we found. So in relationships, we tended to find that things were relatively like consistently grouped into different types of relationships. People might be in familial relationships with each other, and sometimes there was a distinction between direct versus extended family. They might be in community relationships with each other, such as going to the same school or working in the same job, and they might be in romantic relationships with each other. And and often it would make a difference whether it was like interacting with somebody you were previously in a romantic relationship with, somebody who you wanted to be in a romantic relationship with, or someone you were currently in a romantic relationship with. All of those impart different behaviors to the social interactions. For each of these relationship edges in a graph, right? You can kind of think of a relationship graph as like a big database of all the relationships between each pair of characters, but there's still choices for that, right? Like, do you want to make that kind of binary, like the relationship exists or it doesn't, or should it be a scalar? Should it be something where, you can be like 0.5 in a relationship with somebody, and what does that mean, right? How is that realized in the code? Does it have some kind of charge or decay, time-related effects? And then, of course, how do all of the different social interactions affect them? Something interesting in the space of relationships as well, I think there are a lot of systems that kind of try to break it down so that it's not just you are friends with someone or not, and it's not even just a single scalar, but that there's like 3 dimensions to it, right? Prom Week has I believe 3 that kind of boil down to admiration, like how impressed you are by somebody, how cool you think they are. Attraction, so it's like how much you want to be in a romantic relationship with that person, and then affinity, kind of how much you care about a character, how much you care about their well-being and so on. And this allows for more complex types of relationships wherein you can have a great deal of maybe attraction for somebody, but actually not find them particularly cool, or maybe not get along with them very well on an affinity level. And then the next category of phenomena we found that was very frequent in a lot of these simulations, especially in academic settings, was characterizing knowledge phenomena. So in terms of the screenshot is from a game called Roki, which is an adventure game for the Switch. And so this is the kind of thing we see a lot in terms of just what the player has access to, right? This idea of like a journal where as you go through the game and you encounter different observations, you make different observations, you encounter different ideas, your journal will update to kind of keep track of what you know, and so you can revisit that and maybe reuse that information. Well, in social simulation games, I'm actually going to skip a couple of these slides. In social simulation games, such as Elsinore, this game from Golden Glitch, 2016, is a great example of a game where your character is collecting knowledge that you have access to as a player, but then you can also impart that knowledge to the non-player characters, and that might modify their goals and their actions within the game as well. So that, of course, affects the social state and interacts with all of the other things that I've been sharing as well. And kind of none of these phenomena can be really reasoned about or implemented in isolation from each other. And then just to go back to the slide, because it connects back to one of the talks earlier this morning on this track. I have a project with a now graduated PhD student, Marcus Egger, on basically encoding theory of mind, this idea of like reasoning about how other agents will reason about how you reason, and so on. This kind of nested theory of mind, and using that as a way to do AI for social deduction games like One Night Ultimate Werewolf. So that's a project called Ostari that you can check out on my website. And then the next aspect of kind of knowledge, right, that a lot of people are interested in is kind of how people will influence each other's, not necessarily objective knowledge about the world, but their opinions and beliefs, right? Kind of their preferences and how they will make decisions about what goals to adopt and so on. And so we have this simulation called Lyra that basically tries to center this idea of, okay, when characters are in conversation with each other, they might share their points of view with one another on a topic, maybe a political topic such as immigration. They might come in with some bias, some existing kind of opinion about that. And they also, importantly, because of their relationships to each other, might have kind of a group identity with people who have similar opinions to them. So they might be more inclined to listen to people who they think of as themselves as similar to than someone who they don't. So we encoded this model, and we've studied how believable the resulting generated conversations have been from that. So again, like pretty early work, but within the scope of all of these things we've been talking about. Okay, I am running low on time, so I'm just going to mention there are lots of different models of emotion. There are, this has been studied in its own right, kind of in isolation. Just like how different games and simulations will model emotion, what aspects of emotion change over time, how player controls can affect emotion, and how emotion can affect what actions are available to players, and so on. They affect decision making and so on. So we have this descriptive taxonomy, and we're kind of trying to work towards a social physics engine. This is kind of, I feel like, step one in doing that. And my lab has a project called Villanelle, which is an authoring tool that you can actually use and play around with for implementing autonomous characters, not necessarily encoding this kind of rich social model, but where you basically use behavior trees to control what a character in a text-based simulation game will do. And yeah, so I'm hopeful that by kind of trying to characterize what's common among all these things, we will get some better research and development practices, including being able to reproduce the results that we see in academic papers, and yeah, just not having to reinvent the wheel for every new story we want to tell. Yeah, and in the future, I want to say just briefly that people outside of games actually care about this a lot. I'm going to skip over sort of this part, but so far there's been a lot of work in computational social science for kind of trying to understand how, for example, how influence spreads throughout a social network, right? Studies of how people on Twitter might influence one another and change each other's opinions. But for the most part, they've been kind of done at this macro level scale where agents are all interchangeable with one another. You just have, you picture a network and you just see like some nodes with some edges between them, right? And that's your social network. And agents are all interchangeable, and there's not really this kind of like rich modeling of the different types of relationships and social interactions between them. And so like we're interested, and people in computational social science are interested in things that have to do with game theory and economic theory, collective decision making, and influence. At the same time, there is also this kind of disconnect, right, between what we have at the micro level and those phenomena. So things like applications that we might want to explore that involve more kind of fine-grained interactions in conversations, including social skills, healthy relationships, negotiation and argumentation, how things play out in a meeting where important decisions are being made with people who might feel very differently about each other and have different levels of power, and fostering cross-cultural understanding. So there's kind of, there's like a bunch of different work in all of these different directions and not a lot that is unifying them. So that's something that I think is important to keep in mind as we develop games. That basically social interaction is the new 3D graphics, by which I mean like games have done a ton of awesome work that has then fed into what we now use in all kinds of settings outside of games for 3D graphics and VR and all of this stuff. But I really think that social interaction presents another very rich opportunity to do that, to create these social models within our playable settings that are then going to be highly influential and useful outside of the context of strictly play, although play is great as well. So that's it. This is my contact information. I also have a Twitter, which you can follow, and there's the list of games and other resources that I mentioned in this talk, which I highly recommend checking out. And thank you very much.
Right, thank you so much, Chris. That was a very interesting talk, very useful, and it sounds like an immense amount of work to characterize so many features of social agents. Again, thank you for the questions as well. Drop in the panel. We'll take them on at the end of this session. And now we have the third talk of this track, which is going to be by Adith and Brian, about designer-friendly machine learning and RL for video games. So whenever you guys are ready.
I'm ready. Can you see the slides and can you hear me? Perfect. All right. So hello, I'm Adith, a researcher in the reinforcement learning team at MSR Redmond Lab. And together with Brian Broll, who is a research scientist at Vanderbilt University, today we'll talk about making ML and RL friendlier to use in game design and development. A couple of years ago, Brian took a sabbatical from Vanderbilt and joined the MSR AI residency program. At that time, we had all seen the successful demonstrations of AlphaGo, OpenAI 5, etc. We were convinced that ML and RL will play an increasing role in game development. We'll inevitably go from spectacular one-off demonstrations to routine deployments, but much work remains to be done to get there. Today, we'll briefly describe some of the tools, algorithms, environments, and research directions that we have been studying to achieve this vision. So ML and RL agents in games are a reality today. Spectacular demonstrations in StarCraft, research challenges in Minecraft, like the one William just described. It's even shipped in top titles like MotoGP, Killer Instinct, and so on. So the Minecraft example that I'm showing on the slide was actually developed by Brian during the AI residency, and it shows more human-like behavior than previous bots. So we have seen glimpses of exciting new gameplay experiences. And we see the potential for ML and RL to be used more pervasively in the entire game development process, but these techniques also introduce new challenges. At their core, ML and RL are like opaque black boxes, and game developers must somehow figure out how to interpret them and how to influence them. Now, industry has adopted machine learning models in many workflows, so we see several easy-to-use frameworks that support data collection, training, evaluation, serving of ML models. Even for reinforcement learning, there are now workflows, for example, in Azure Machine Learning, that supports distributed deep RL training and serving. But there is a big gulf between the worldview implied by these 7 steps workflows and the world inhabited by a game developer. So a game designer or an AI developer is typically trying to accomplish some game concept, some desired vision, or some emergent gameplay or behavior. And this is very difficult to frame in terms of reward functions or evaluating predictions of an ML model. So there are many rounds of trial and error. For example, as we try out many different action space definitions in this StarCraft example, and then we run ML or RL only to discover some new unanticipated failure mode. When we view this as a developer interacting with an opaque partner, we can distill the challenges to 2 issues. How can the designer understand what their opaque partner is doing? And how can the designer influence that opaque partner to do their bidding? So the plan for the rest of the talk is to highlight 3 directions that we have studied to make ML and RL more accessible for game development. The first direction addresses the interpret direction of that loop. Can developers understand the emergent behavior of learned models and agents? So Brian will first describe tools for visualizing bot behaviors in Minecraft. These tools have now been incorporated into the Game Intelligence project repo led by MSR Cambridge. The second direction addresses the influence side of that loop. So can we make ML and RL agents obey the designer's intent better? I will describe learning algorithms which allow designers to get controllable generation of agent behaviors. This was a collaboration with Professor Yisong Yue's group at Caltech, and it was presented at the ICML conference last year. The final direction addresses the interaction loop more holistically, and Brian will introduce a new environment to study ML and RL in games. This project is developed with the open source strategy game 080 and offers an intriguing testbed for future research. Over to Brian for the first research direction.
So, as Adith mentioned, I was working on creating more human-like AI during my residency at Microsoft Research. Evaluating if the behavior was human-like led me to watching many individual rollouts of various models. This was quite time-consuming and still unsatisfactory even when the agent exhibited the desired behavior. I found myself wondering if the agent in fact learned to play more human-like, or if I simply got lucky during that rollout. This led me to think about how we gain confidence in complex systems such as large software systems. In many ways, a single rollout is a lot like a unit test. Could we gain inspiration from other software testing techniques for establishing more intuition and confidence in our trained agents' behavior? Generative testing techniques were one such inspiration. Rather than focusing on individual test cases, or rollouts in our case, we should be able to consider domains of input or dimensions of interest and then explore them more thoroughly. To make this a little more concrete, here's a video of a single rollout. This video shows a bird's eye view of a scenario in Minecraft. The agent is shown in light blue and the enemies are shown in green. The dot inside the blue circle is displaying the action that would have been taken by the agent in this rollout. And in this single rollout, we can see the agent getting attacked by the enemies and retreating until it ends up getting cornered and defeated. Now, this shows the counterfactual dashboard that I developed for understanding learned agent behavior in this Minecraft scenario. Inspired by generative programming, I wanted to understand the agent's learned behavior across different locations in the current scene. So the point grid here represents alternative agent locations and the corresponding agent behavior if it were in those locations. Movement is designated using the arrows, and colors correspond to other types of actions such as attacking or using items. Visualizing these counterfactual states across dimensions of interest, in this case the agent's location, allowed me to gain insight into specific shortcomings of the agent. In the earlier portions of this video, the actions are relatively smooth. In other words, there are few drastic changes when moving from one counterfactual position to a neighbor. Similarly, actions don't change drastically from one frame to the next. However, when the enemies have surrounded the agents and are attacking it towards the end of the clip, we notice that this is no longer the case. The behavior of the agent is much more erratic and sensitive to subtle changes in position as well as between frames. I realized that these situations are uncommon in the training data and would benefit from collecting more data around these sorts of situations. This is just one insight that can be gained from this rollout using the counterfactual dashboard. Rather than gaining insight from a single rollout at a time, counterfactual visualization allows us to specify dimensions of interest in the state space, like the agent's location in this case, and visualize the agent's behavior across the given dimension within a rollout. Over to Adith for the second research direction.
Thanks, Brian. In this next research direction, we asked how a designer might control abstract aspects of AI agents, like how aggressive or defensive they are, or what their skill level is, or have them prefer a certain play style, etc. Having an RL agent that can play a game to a superhuman level is mighty impressive, but it's definitely not fun for me if I'm always losing to the bots. So imagine instead there was a control knob to tune my opponent, so that when I'm in the mood for a passive skirmish, I get an AI like the incompetent Black Knight from Monty Python, or I can turn the aggressiveness dial all the way up and fight the trigger-happy fellow from Wolf 3D for a real challenge. Now, this functionality of controllable generation has been demonstrated for text and images. OpenAI has impressive demos of language generation using GPT, and deepfakes can easily manipulate aspects of portraits like gender, ethnicity, hairstyles, etc. Can we do the same for gameplay? So we looked at player trajectories in many different domains, in Minecraft, in Atari, real-world basketball players, to build intuition for what play styles and variations might actually look like. So we quickly realized that the what to control, these knobs like gender or ethnicity or hairstyle in images, the analog of that for behaviors is best defined by the game developer. So take, for example, controlling how a player moves on a basketball court. I want to specify some high-level aspects of movement, like the destination the player is going to, how quickly they move, how far from their assigned court position, etc. A nice feature of many of these aspects is that they have the I know it when I see it quality. So given a trajectory, I can tell you afterwards whether the displacement was a lot or a very little. So we borrow a concept from weak supervision in machine learning, labeling functions, to capture this intuition. A developer specifies a control knob by supplying a labeling function for it. The knobs can be imprecise, they can be noisy, a collection of them may be mutually contradictory, etc. No problem. It's the algorithm's job to ensure that behaviors generated by an agent are consistent with the norms. So we developed a self-consistency check that is performed throughout the agent's learning process to influence the agent's policy. The key insight is that labeling functions need not only be applied to human demonstrations. They can be applied to arbitrary rollouts to give a weak, noisy training signal. So here is the algorithm in a picture. We sample a setting for the different knobs and feed them as a control signal to the agent. We collect a rollout from the agent acting in the environment. We apply the labeling functions to the rollout and check whether they give us the same value as our control setting. And if not, we have an error and we backpropagate this error through to the agent's policy, in addition to the other standard machine learning errors that it's optimizing. We experimented with an imitation learning agent that was trained using a diverse collection of real-world basketball player movements provided by stats. So we found that the style consistency check from the previous slide was crucial. Without that, using state-of-the-art techniques from the image generation literature gave us results like the one you see on the left. So every trajectory ending in a red dot here indicates that the policy did not actually obey the desired control setting. In this case, we kind of wanted high displacement from the initial code position. Whereas the style consistent policies that we trained always obey these styles and without compromising any of the imitation quality given our diverse collection of real world data. So there is an online demo that you can check out at the basketballai.com website. In the paper, we also show that we can push this technique to give controllable generation for 1,000+ styles. Basically, we had 5 knobs, each with 4 different settings. So 4 to the power of 5 gave us 1,024 styles. And we described an imitation learning approach so far. Please see this blog post and the associated paper from the MSR Cambridge lab for follow-ups that study this in an oral setting. Our bet is that controllable AI agents is going to be a very fertile and impactful avenue for future research. And now I'll hand it back to Brian.
Thanks, Adith. So far, we've been looking at how machine learning can assist in designing individual agents. Specifically, we now have agents with many different parameters, and we're using machine learning techniques to discover a set of parameters that results in desirable behavior. In fact, this problem is quite similar to game design and balance itself. Games contain many different parameters that need to be set appropriately to achieve the desired gameplay experience. This is particularly challenging as small changes can have drastic impacts on player behavior. Let's illustrate this with an example. Suppose I wanted to determine the attack speed for cavalry in a simple RTS game. In this game, I have decided that a cavalry army should be defeated by a spearman army of equal economic value. Conceptually, one approach could be to set different attack speeds and just check who wins between the two armies. We should be able to find a maximum attack speed where the cavalry are just barely defeated by the spearmen. Then we can pick any attack speed less than this value, and we might assume that it will work. Here's an example of this approach. The video on top shows us searching for the maximum attack speed where we still lose to the spearmen. After finding the maximum attack speed, we'll simply select some attack speed less than the maximum that we found and use that in our game. However, this approach is a bit problematic because the cavalry are simply charging in and attacking the spearmen every time. When we move on to playtesting, the human players are likely to employ more sophisticated strategies, such as kiting shown on the bottom. This is because automated game balance requires a more sophisticated approach. Evaluating game design entails understanding on some level how humans will interact with the game, such as through modeling players or perhaps types of players. However, humans are quite good at exploiting particular game dynamics and can be difficult to model, especially in environments supporting rich, diverse playstyles and strategies that are commonly found in games. This is a hard problem, but it's also a problem that game designers face every day. This makes a huge opportunity for novel, impactful research. But how can researchers even explore this problem? Researchers need an environment with an active player base where they can modify the game parameters and evaluate the resultant game design. The environment must support defining smaller scope scenarios, as in Minecraft. We present ZeroAD as that sandbox to explore game design and balance questions. ZeroAD is an open source RTS similar to Age of Empires, into which we recently integrated an interface for reinforcement learning and game balancing. All game parameters are readily available and can be modified from Python. As it is a game with a player base, player replay data is also available. Over 1,000 replays are available in the link at the beginning of this section. Creating custom scenarios is also possible using the existing visual editors and tools provided by ZeroAD itself. Any custom scenarios can then be used to either collect human replays or for training RL agents. These capabilities make it possible to explore fundamental questions around game balance, including player modeling and counterfactual reasoning. In fact, the videos from the previous slides were created using this sandbox. As this environment also supports mods, we can revisit the earlier questions of agent visualization, calibration, and even study richer forms of interaction between the developer and agents. Really, the sky's the limit. Taking a step back, we've seen examples of 3 projects. First, we explored developer-friendly interpretation and exploration of agent behavior. After understanding the behavior, we presented one direction by which the developer can influence the behavior via semantically meaningful calibration knobs. In the third project, we discussed game design exploration and a sandbox in which we can readily explore these questions. Each of these projects reveals fundamental questions for future research. On visualization, how can we leverage lessons learned in understanding large, complex systems and empower developers to gain a rich understanding of agent behavior? On calibration, perhaps we've offloaded too much to the developer to define control knobs and their corresponding labeling functions. How might we go after more abstract control knobs? In conclusion, we believe these three projects illustrate exciting frontiers that contain research questions that are both challenging and huge opportunities for impact. Game design and playtesting is very time-consuming. The biggest opportunity is leveraging AI to drastically reduce the time spent on this part of the development process. There are many challenges in the work discussed today, and it's difficult to select the grandest. That said, player modeling in these rich environments is particularly noteworthy. Before we open for questions, we have a few questions of our own for game designers. How do you currently specify design constraints and goals such as expected game dynamics? What are some examples of these constraints? Could we capture some of these types of constraints with a few benchmark scenarios? And are there any player characterizations already used for playtesters? With that, I would like to thank you for your time and hand it over to Diego to open it up for questions.
Thank you, Brian. Right, so this was a set of very nice talks. I'd like to thank again all the speakers. Now we are ready to take all the questions, or some of the questions. We have about 9 minutes to finish this session. So we're going to start with Will and Stephanie. There's a question that says, what could the MineRL organizers see as the main learnings from this year's competition, and what are the remaining opening challenges?
Great. Yeah, I'll go ahead and jump into what we learned this year, and hopefully Steph can talk about some open challenges. So I think the biggest lesson we've been taken away from the MineRL competition is that if you pose the challenge correctly, if you pose RL competitions correctly, you actually have a very good chance at lowering the barriers to access for hard RL competitions and RL research in general. So one of the things that we first learned is that hard tasks can be solved with relatively small amounts of compute. It's very, very surprising to us that the obtained diamond task can, yield any sort of reinforcement learning reward after, 8 million samples in the environment. And usually if you just throw PPO at this problem, it's going to be something like, hundreds of millions of samples to billions of samples to start getting good performance. So posing the RL competition correctly, limiting compute, it actually really enables a lot of progress in this extent. The other thing that we find is really useful is sort of that when you do obfuscation, domain expertise and inductive bias are not going to sort of skew competition results. So in a lot of competitions, if you know a lot about, for example, musculoskeletal, behavior and physics, you can, solve the musculoskeletal RO challenge with relatively good performance because you impute that inductive bias on the problem. But if you use, domain obfuscation using sort of, for example, the technique we used in our sort of competition with the random autoencoder, it'll go a long way in preventing these solutions to be so domain specific. And in fact, over last year's competition, we really did not have the same action shaping. No one was saying, move forward, craft, and then, look down, because that's what you do after you craft the pickaxe. And so you get a lot of sort of agnosticism out of that behavior. I think one of the biggest lessons as well, and probably the final one, is that imitation learning works way better than you would expect. This is huge because if you sort of have competitions that are run purely on imitation learning, you really lower the barrier to entry. People with massive amounts of compute really don't succeed in comparison to these imitation learning techniques a lot of the time. And we saw that with our third place pointer being an imitation learning technique. So yeah, Steph, I'm curious to hear what your thoughts on open challenges are.
Yeah, thanks, Will. As for open challenges, of course, the central problem of the competition, obtaining a diamond in Minecraft, still hasn't been solved. But more generally, I think some open problems include all of those that the competition itself kind of generally poses, like performing intelligent exploration, learning in a sample-efficient manner, and finding good and transferable representations of the environment. Additionally, we're also interested in exploring the multi-agent setting. So, for example, like human-in-the-loop tasks, And in these settings, there are even more challenges like communication and teamwork that we think are really interesting to explore. Thanks.
Right, thank you. We have the next question for Chris. So Chris, thanks for the great talk. Looking at recent insights from cognitive science and psychology, are there any directions that you find particularly promising as a basis for the social simulation engine that you're describing?
Yeah, thanks for the question. I think there's no single, what my talk covered was so many different phenomena that come into play with social interactions that there's not really a single, I guess I would say a single theory that people are trying to operationalize. But I think like there are some really interesting foundations that these existing projects have built on. So one that I know is the foundation for a couple of games and systems is Roger Schenk's concept of scripts, which is actually a sort of an old AI thing. But this idea of social scripts, where people kind of have templates for interactions that they believe to be in the scope of the activity that they're doing, as opposed to just considering the space of all possible actions within an environment. I think that's been a very powerful idea and useful for abstraction. And I think there's also been some really interesting implementation of like kind of theories of social norms and how we adopt social norms and the sort of social responses to when somebody flouts a social norm. And that's actually the kind of thing that I'd be really interested in seeing more computational implementations of, because I think currently people people just wind up embedding social norms as kind of programmatic exclusion of possibility for action in their systems, whereas you could actually do something kind of interesting with permitting social norms, but having people react, like having other agents in the simulation react to that in a believable way. Thanks.
All right. And as a follow-up for a different question that was very highly voted, do you know of any public data sets of agent environments for experimenting with this sort of social and conversational agents?
Yeah, so I mean, I think it really depends on what you want to do. A lot of the results of what we found is that there isn't a single data set or source of interactions that's really going to make sense for all contexts. People have come up with totally different ones for not just different types of stories, but different stories, different games that they're actually trying to create. But hopefully, once our work is accepted for publication, we'll also release the data set of all of the common features that we found and work on implementing that as an engine. I will say that if you're just looking for something to play around with, there is a population simulation engine called Talk of the Town by James Ryan, which is on GitHub, and that's available open source. And likewise, my student, Sasha Azad, if you go to her GitHub page, I wish I could type things that everybody could see, but on Sasha's GitHub page, the implementation for Lyra, the opinion change model, is also openly available.
All right, thank you. We're going to go with the last question that we have time for this session. This is for Adith and Brian. And the question is, how do you label the data for the knobs in the behavior?
So I mentioned labeling functions. So this is a very powerful concept that was developed for supervised learning or weak supervision. The idea is we are not sitting down and having developers look at individual behaviors and label them one by one for each of the knobs. The idea is that the developer provides labeling functions. Take, for example, destination, right? I simply measure properties of the trajectory and verify whether the destination actually satisfies the goal that I specified or not. And turns out you can write down very simple functions to capture many different things like destination, speed, displacement, stuff like that. Like many things that have the I know it when I see it property. There is a big opportunity to try to figure out a translation layer between that and more abstract concepts like aggressive play style, right? I doubt that I'll be able to quantify it as a single setting for how many attacking units I produce, and figuring out a way to translate to more abstract control knobs is an interesting avenue for future research. But for this work, through labeling functions, basically. These small, simple snippets that take an entire trajectory and give you either a label per time step or a label for the entire trajectory.
All right. Thank you so much, Adith. Unfortunately, we have no more time. So I'd like to thank you again, all the speakers, Will, Stephanie, Chris, Adith, and Brian, and all the people in the audience for posting questions and participating in the session. We are now going to move to the final session of the day, which is the Game Studio Plenary. And this session will start at 1:30 p.m. Note that you may have to move to a different Teams live link for that session, but essentially you can change the link in the slide that should be showing up there. It's up there already. Fantastic. So yeah, thank you everyone, and see you there.